Hello everybody, welcome to my final project. This is the Mandelbrot Explorer and I am Austin Carbajal. If you're unfamiliar with the Mandelbrot set, it's a two-dimensional set with a relatively simple definition that exhibits a lot of complexity, especially as it's magnified and around its boundary. It's very popular for its aesthetic appeal and the amazing fractal structures that it produces. The Mandelbrot set is defined in the complex plane, the complex number c, for which the function f of z equals z squared plus c does not diverge to infinity when iterated starting at z equals 0. This graphic by 3 blue 1 brown really helps to visualize what that trajectory of the complex number c is doing. Depending on where you start, sometimes it converges to 0, other times it explodes and goes off to infinity. What we really care about here is the number of iterations that it takes to either converge or diverge. So, for my project, I build a device that takes each and every pixel on the screen, maps it to a spot in the complex plane, and then calculates whether or not it's part of the Mandelbrot set. After a lot of Verilog learning, I was able to get this image here. I wasn't really sure how I was going to go about this video as a demo, but I've decided to treat it more as an art project than anything. So the first thing that I did to this image was give it the ability to colorize itself. The device takes each complex number c and iterates it over and over again until one of two things happens. Either z exceeds 2 or it reaches 2056 iterations. If one of those two conditions are met, we deem that it is not within the set. If it's not within the set, we take the number of iterations that it took for z to reach 2 and we assign a color to it based on that number of iterations. I wasn't happy with just one color, so I decided to give the device the ability to rotate through different color palettes. Each color palette contains 256 individual colors that are assigned to a number of iterations that it took for z to exceed 2. Here's a graphic that demonstrates the 7 color palettes I ended up going with. These color palettes can be cycled by using switches 7, 8, and 9. Now, it wouldn't really be much of an explorer if you couldn't actually explore. Switches 0, 1, 2, and 3 allow you to pan up, down, left, and right. Then buttons 1 and 2 give you a zoom in and zoom out feature, each time by a factor of 2. It's capable of zooming in a total of 14 times for a total magnification of 16,384 times its original size. As you probably noticed in that clip, the Mandelbrot set contains a bunch of miniature Mandelbrot sets. Here's one of those just colorized in the different palettes. The different palettes allow you to see different details within the fractal. Here I actually discovered that if you don't assign enough colors per iterations, the device will take the last known color and drag it across the screen until it reaches another iteration that it's able to calculate. It creates kind of a cool effect. But that doesn't really hold true to the nature of the Mandelbrot set, so I fixed it. Another feature I added was the ability to assign color based on a logarithmic scale as opposed to a linear scale. The top two images here were assigned based on a logarithmic scale, and as you can see, they define different details in different areas of the fractal. Both can be equally as effective, just for different scenarios. That ability to switch is assigned to switch 5. Switch number 4 actually gives you the ability to explore an entirely new fractal. This is the Burning Ship fractal, very aptly named. It's calculated by taking the absolute value of z and iterating that instead of z itself. As you dive deeper and deeper into the Mandelbrot set, the structures become infinitely more complex. The following images are just a collection of structures that I found while exploring. I'll be quiet now and let you enjoy those for a moment. As you can see, there really are an infinite number of structures within the Mandelbrot set, and we've barely scratched the surface. Some are far more chaotic than others, and I think that they're all beautiful in their own way. This project has taught me a lot about the limitations of digital hardware design. The first issue I ran into was just with the arithmetic. Having to calculate values down to the 32nd, 33rd decimal place, I ended up having to create my own modified fixed point arithmetic. This device truly taught me how important optimization can be. With each pixel making multiple calculations, potentially up to 2,000 times, that adds up. The first version of this design utilized a single engine to calculate the entire Mandelbrot set. That took approximately 2 seconds per screen refresh and created a very, very clunky user interface. With the resources available on the board, I was able to utilize 5 engines in parallel. I also took some time to optimize and reduce the amount of clock cycles per calculation. Together, these things helped a lot. After everything was put together, I discovered that I had some pretty serious timing issues. Using the built-in timing analysis tool, I was able to discover that one of my pathways had a setup slack of about negative 12 nanoseconds. After tracing those data paths, doing some effective pipelining, and then using onboard DSPs instead of the regular multiply function, I was able to get that timing back in check. All in all, this project was a great learning experience, and I had a lot of fun exploring the set. And if you've been paying attention, you might have realized that we haven't used Switch 6 yet. You might also be saying to yourself, I don't know how this project could get any cooler. Well, let's hit it with some sax and see what Switch 6 does.
Like I'm dreaming, like I'm walking by your side, keeps on repeating, so free all the talking, wasting all your time. I've given all, but I've got if you want.